Okay, nerds, after yesterday's atrocious test, we got to continue learning more trigonometry and hope that with learning the new stuff, the old stuff gets better.
Hopefully.
That way, the new test at the end of the unit could overwrite the last test and we could boost all the grades. That would be the hope. Anyway, vocabulary. The tangent function maps all the values of tangent of theta. Okay, tangent of theta in geometry you might have learned using SOHCAHTOA is opposite over adjacent. Of course, we saw that anytime something is on one of the quadrantals, opposite over adjacent doesn't make sense anymore. So instead we use x, y, and r. And what we said was that tangent of theta is y over r. But in the unit circle, y is sine of theta, x is cosine. I said y over r, didn't I? Tangent of theta is y over x. I think I said y over r. Anyway, y over x. In a unit circle, y is sine of theta and x is cosine of theta, which means tangent is sine of theta over cosine theta, which is really cool. And because it's a fraction that has something on the bottom that has the ability to be 0, tangent of theta has the ability to be undefined. And it's going to happen whenever cosine of theta was 0. So there will be vertical asymptotes every time cosine of theta would have been 0. We don't call the graph of a tangent function a wave. Only sine and cosine are waves. We just say it's the tangent graph or the tangent function or the tangent curve. Okay? We also, I'm recording, I can't. Dad jokes later. We also can't say the amplitude of tangent. That doesn't make any sense. And the reason why is because the amplitude is literally the maximum or minimum distance from a midline. But tangent has vertical asymptotes. And the definition of vertical asymptote is a place where your graph will get insanely close, but will shoot off towards one of the two infinities. That's why they're called infinite discontinuities, if you remember back to the beginning of the year. And since our graph can shoot off to the infinities, the range of tangent is all real numbers. So it doesn't make any sense to say its amplitude because it doesn't have a maximum or a minimum. The number on the front is literally just a stretch or a shrink. That's all it is. We also can't say the midline of tangent. The reason why is because the midline is the line that is halfway between the maximum and minimum, and since tangent has neither a maximum nor a minimum, it does not have a midline. However, we will still care about the horizontal line that goes through the dead middle of the graph. Because just like sine and cosine, tangent has inflection points on that horizontal line. So we'll just call it the line where the inflection points are, or something like that, okay? For the parent function, that is the x-axis, just like for the parent sine wave and the parent cosine wave. Will I slip up every now and then and say the midline of tangent? Yes. Will I slip up every now and then and say the tangent wave? Yes. They just realize that those are wrong, and I'll try to correct myself because you can't say the amplitude, the midline, or call it a tangent wave. Okay? Okay. So, boop. This first question is asking us to fill out this table of values using our memorized unit circle, but if you are like me, you do not have the unit circle memorized because I showed you, you could just know your two special right triangles and use reflections of them and just do your y over your x. That's a little bit confusing here because you see y and x here. Understand what I'm talking about is angle x, not side length x. Okay? So what we're doing here is we're using x to represent our angle variable. And this y value is taking on the ratio of the triangle that you could draw at this angle's y over x. I know that's confusing. I'm sorry. This is ratio y, not side length y. This is angle x, not side length x. Cool beans? Great. No, I don't have my unit circle memorized, but I can get these values relatively easily. Here, at 0 in the unit circle, you're on the x-axis. What is the y value when you're on the x-axis? 0. And since tangent of theta is y over x, we have 0 over x, giving us a tangent value of 0 at 0 radians. Cool beans? Great. You know where else that happens? In the unit circle? at pi, the other side of the x-axis. There. Since we're talking about things that could equal 0, what about on the y-axis in the unit circle? Here at pi over 2. If you're on the y-axis, what does x equal? 0. And since tangent is side length y over side length x, that's side length y over 0, which means this is undefined. Okay, so now let's move on to the triangles we could draw. At pi over 6, this is a 30-degree angle. That means the side across from it, the opposite, is the 1. Adjacent to it is the root 3, so this is 1 over root 3. If you reflect pi over 6 into quadrant 2, you land at 5 pi over 6. Tangent's negative in quadrant 2, though. This is a 45, 45, 90 triangle in quadrant 1. The side length x and side length y are equal to each other because it's isosceles. So tangent there is equal to 1. If you reflect pi over 4's triangle into quadrant 2, you're at 3 pi over 4. Tangent's negative in quadrant 2, though. And pi over 3. This is the 60-degree angle. Across from, opposite, from the 60 is the root 3. Adjacent to it is the 1. So root 3 over 1. And if you reflect pi over 3 into quadrant 2, you're at 2 pi over 3, but tangent's negative in quadrant 2. There. So no, I don't have the unit circle memorized, but I can run through the triangles in my head pretty quickly. Speaking of tangents negative in quadrant 2, I want to bring you back to what we did a while back. This is unit circle, and this is where things are positive. ASTC. Tangent's positive in quadrant 1 and quadrant 3. Tangent's negative in quadrant 2 and quadrant 4. Okay. So let's check out this example B. Is to state the intervals where the intervals of x, where our y values are increasing. Remember, increasing and decreasing, College Board wants those to have brackets on them. So it would appear as though we begin increasing at 0. And we're going to increase up to the point where we're undefined. But undefined is a place where the graph doesn't exist. It's a discontinuity. So I can't put a bracket on it because the graph doesn't exist there. But if you look just past it, look at this. They're increasing again. All the way up to pi. So where is it decreasing? Never. Never. The parent tangent graph is an always increasing function. So it's never decreasing. Now, could we transform it and make it decrease? Of course we could. But the parent graph does not decrease. Yes, sir? Y is what? Oh, I just goofed. Sorry. As I was already thinking ahead to the next step. This is weird. Having a discontinuity in the dead middle of this table, isn't it? Strange. So weird. It's so weird. So I'll tell you what we're going to do. Let us go ahead and plot most of the values we just had in that table. Most of them. Okay? We knew that we had 0 at 0. I'm not going to try to put the pi over 3 or pi over 6 on here because you'll notice this thing is going by pi over 4s, right? At pi over 4, tangent was 1. At pi over 2, tangent was undefined. Again, I'm not going to put the pi over 6s or pi over 3s on, but the next one is 3 pi over 4, where tangent was negative 1. So this is all from that table we just had. And then we were again 0 at pi. And that was everything in our table other than the pi over 3 and pi over 6. Cool? All right. So what's going on here? Well, we have to think all the way back to the beginning of the year and what it means to be an infinite discontinuity. It's a place where your graph shoots towards one of the infinities, and you will get infinitely close to that vertical asymptote. And we know these things are curvy because circles be round, so tangent is going to be curvy, like sine and cosine are. So it does this. Wee. And wee. That's really weird. But here's what I know. In quadrant 3, tangent's positive again. But all of its values would be exactly the same as they were in quadrant 1. So quadrant 3 is a copy of quadrant 1. And every time we're on the y-axis in the unit circle, we're undefined. So let me put a copy of quadrant 1 into quadrant 3. And then I can copy quadrant 2 into quadrant 4. And if I could do that going right, I could do the same thing going left. Because tangent is positive in quadrant 1 and then positive again in quadrant 3, tangent's values repeat themselves more than once in a full circle. They repeat themselves twice. That means in a full circle, tangent goes through 2 of its periods. So the period length of tangent is not 2 pi. It is pi. The period length of tangent is pi. And that has implications for us when we try to find its period length using transformations. So we will no longer say 2 pi over b. Not for tangent, at least. We'll say pi over b. Transformations work the same on all functions. It just means you need to know the difference between sine, cosine, and tangent. Okay. But it says on what continuous interval can we see the entire behavior of the function? Meaning, from this x to this x, we can see every value that tangent can take on. What would you say? And continuous means you don't have an asymptote in the middle of it. So from where to where? Adi? Negative pi over 2 to positive pi over 2. And this is going to be considered the parent curve on that interval. Because that shows you every possible value it can take on. The next thing says, find the inflection points. Well, tangent has an infinite number of inflection points just like sine and cosine do. What's really cool about it is, just like sine and cosine, those inflection points are found on a horizontal line that you could draw through the middle of it. I can't call it its midline, but it behaves like one. And look at this. Everything above that middle line is concave up. And everything below that middle line is concave down. So the inflection points are always going to happen on that middle line. It's not a midline. It's the horizontal line that we draw right through the middle. It behaves like a midline. Okay. So how do we label them? Well, let's look where they are. Negative 2 pi, negative pi, 0 pi, 2 pi, 3 pi, 4 pi, 5 pi, 6 pi, 7 pi, so on and so forth. The inflection points are always going to be found at x equals whole multiples of pi in pi, where in is an integer, positive or negative. You don't have to even write plus or minus. When you say in is an integer, that includes positive and negative. You're not wrong to say plus or minus, but it's not necessary because integers can take on positive and negative values. Now, something that's really neat is this is not the first time that inflection points have been found at all of the whole multiples of pi. Do you know what other trig function does that? Sine does. It's where sine hits its midline. So why does tangent have this property in common with sine? It was because tangent is sine over cosine. So it behaves somewhat like the sine wave does. Someone in second period said, well, what properties does it inherit from the cosine wave? And I go, well, it's undefined everywhere where the cosine wave is on its midline, because that's where cosine would have been equal to 0. So yes, it has both properties, but it specifically matches the property of sine where it has its midline hits, if you want to call it its midline for tangent, okay? Okay, so what is the domain? Well, the domain is basically this, but repeated every plus or minus whole multiple of pi. So we'll write it like, and I don't have to say plus or minus, and let's just up here write that n is an element of the integers. That way, every time I write an n, we just know that means it could have been a positive or negative whole number. Cool? So our domain is from this plus period any number of times to this plus period any number of times, as long as n is the same number for both. But because this thing reaches towards vertical asymptotes, also known as infinite discontinuities, the range is infinite, up and down, all real numbers. The parent tangent function has x-intercepts that are inflection points, so they are going to happen at n pi comma 0. Of course, that's where n is any positive or negative integer. But it has a single y-intercept. Happens to go through 0, 0. Tangent, like sine, is an odd function. It has odd symmetry. What does odd symmetry mean? It means if you could spin your graph around the origin 180 degrees and have the exact same image, it is an odd function. That's what that means. It's the same thing as saying if I reflect it over the x, that's the same as reflecting it over the y, which is actually what I'm going to write here. That tangent of negative theta reflecting over the y is the same thing as negative tangent of theta reflecting over the x. That was the exact same property that we had for sine of theta, because it's odd. So reflection on the inside, it's kind of a pain in the butt. Move it to the outside. We'll say it's a reflection on the outside. Reflect on the inside and the outside, that's the same as doing nothing. The asymptotes. Okay? Well, the asymptotes are happening at every odd pi over 2. Or you could say the first one, it's got an infinite number of them. Who's to say one is the first one, one is the, whatever. You could say it like this. Vertical asymptotes are going to occur every time x is pi over 2 plus any number of period lengths. And obviously that means plus or minus because n could have been a negative number. Because integer means positive and negative. So this setup is all odd pi over 2s. In period 2, I showed it differently. And then one of the students, I think it was Chris Jansen, he was like, how is what you did different from this? And I was like, they're not, they're the same. Because in period 2, I described it as all the odd multiples of pi over 2. So I wrote this as one fraction. But that may or may not have been confusing for some people. I don't know. And these key points, I'm not going to list them out. I'm just going to show you where they are. They are asymptote, -1, inflection point, +1, asymptote. There they are. All we care about are the asymptotes, the inflection points, and the ones, positive and -1. Those are the 5 critical values or whatever. I don't have them memorized. I have the shape memorized, just like I do for sine and cosine. The shape I memorize for tangent is that. I know that that is what the parent tangent function looks like. I can reflect it, and of course I can shift it. Of course I can stretch it and shrink it in both directions, but that's what the parent one looks like. And I know that this is an inflection point, and I know that between the inflection point and the asymptotes, I need to care about a 1 and a -1. Of course, a vertical dilation would affect the 1 and -1. Throw a 2 on the front, now it doesn't go to 1 and -1, now it goes to 2 and -2. But that's the same effect that transformations have on all functions. Tangent is not special when it comes to transformations. Boop, boop. So let us get down here and let's graph negative tangent of x. Well, I mean, that's just a reflection over the x-axis. Reflect over x-axis. That means turn the graph upside down. So none of the inflection points are going to move, and none of the asymptotes are going to move. Poop. I started putting my red dots in the wrong spot. Got ahead of myself. I have an inflection point halfway between every asymptote. I have an asymptote halfway between all of the inflection points. Isn't that neat? So halfway between two asymptotes, an inflection point. Halfway between two inflection points, an asymptote. Pretty nice, right? And I know that halfway between an inflection point and an asymptote is either a 1 or a -1. Since this graph is upside down, it does this. And that will just repeat over and over and over again. Ta-da! This graph is always decreasing. It didn't ask, but it is. It's always decreasing. You know what? Screw it. Let's write it. Always decreasing. On its domain, obviously, the asymptotes don't count because they're not part of the graph. Not bad, right? Cool. Can I flip it? Nobody's going to panic? I don't want to move too fast for anybody. Okay. Let me tell you, whoa, there's a loud noise back there. Let me tell you how much of this I have memorized. I have this shape memorized. That's about it. And I just recognize that from asymptote to asymptote is the period. And I know that from inflection point to asymptote is half period. And I know that this number is going to be whatever the A value is on the front. And this number will be whatever the A value is on the front, but negative. Now, obviously, if the graph is upside down, the X value where it occurs is going to change. But what I do know for a fact is that from inflection point to one of the ones is always a quarter of the period. But I don't even try to figure out quarter of period. I literally will draw these, then I'll plot that, and then I'll go halfway between them. So is it a quarter of the period? Can you split the thing into quote-unquote fourths? Sure you can, just like sine and cosine. But that isn't 4 quadrants. That's actually 2 quadrants. So I think it's a little bit more confusing to do it that way. I don't know. There's some stuff here. I've never even read those words. They're not important, as long as you recognize the shape. So do I have this crap memorized? Freaking no. No, not at all. And I've never needed to. I don't use that kind of knowledge. And right here where it wants me to use the letters to write generalities, do I know any of that? Well, I know one of the 5 things that's on here. Here's what I know. The period is pi over b. I know that. But that's just because the period length is pi. This over b is just a transformation. I'm not going to worry about the other stuff. I mean, the range is all real numbers. I know that. That's true for all tangent functions. But this key points baloney, look, the only thing I really care about is what makes the inside equal 0. And the reason why is because right here, the inflection point is always going to make the inside equal 0. Always. So long as you know what makes the inside equal 0 and you know the length of the period, you are set. It's all you need to, and then you need to see what the A value is. You're set. Shape, see the A value, know the period length, tell me where it makes the inside equal 0, golden. Very easy to graph. And then there's some other stuff. I don't know. None of that matters. Okay? This one. First things first, just like with sine and cosine, I want to talk about its shape. What do I see? It's been reflected, and it actually doesn't matter if it's up, down, or left, right, because tangent is odd. Its shape is like this. I know that the inflection point makes the inside equal 0, but it's upside down. So where is that inflection point? What makes the inside equal 0? Well, 0, yeah. Okay. Now let's figure out our period length. Period is pi over b, which is pi over 1/2, which is 2 pi. This thing has a period length of 2 pi. I know its shape, I know where to find an inflection point, and I know how far away the next inflection point will be because it repeats itself every 2 pi. So I put my first inflection point on there, and then I go one period away to find the next inflection point. And you can do that in both directions. See how I did that? I just went 2 pi to the right and 2 pi to the left. That's the period length. And guess what's going to be found halfway between inflection points? Asymptotes. Great. Halfway between asymptotes is going to be either a 1 or a -1 because the A value is 1. We've already talked about the fact that it's negative. That's why it's upside down. So it's either going to be a 1 or a -1. But since it's upside down, clearly I have to go left and up. So halfway between a dot and an asymptote, go up to +1. And over here, halfway between the two, go down to -1. And there it is. And then just repeat on the other side of the asymptotes, and you're ready to rock and roll. Nice wide tangent function. Almost said wave. There it is. See, we're not graphing the √3s and the 1 over √3s. Who cares? Not important. Questions, comments, concerns about that? It's not bad, is it? In some ways, tangents is even easier to graph than sine and cosine. If there's no freakouts, we'll do the next one. Okay. No reflections this time, which means our tangent function goes up and to the right, down and to the left. And we know that whatever makes the inside equal 0 will be that inflection point. What makes our inside equal 0? Come on, guys. 0 again. Great. So yeah, I'm just going to put a green dot there right now. I already know what's there. But now let's track down period length. Pi over b is pi over pi fourths. Whew. I'm sorry? Oh, no, the x is just x. We're just using the number in front of x. In case you don't see it, that's like saying pi over 1 times 4 over pi, and the pi's cancel, and you get a period length of 4. Remember the whole keep, change, flip crap? That means if I go 4 to the right or 4 to the left, I find another inflection point. 4 to the right, 4 to the left. And halfway between inflection points are vertical asymptotes. And my ones and negative ones are found halfway between the inflection points and the asymptotes because, again, the A value is 1. You know what? You want to make this a better picture? I mean, a better example? Because I don't think... Yeah, this is the last example. I'll tell you what we're going to do. We're going to deviate a little bit. We're going to do this. Boop. Let's throw a 2 on the front of it. Unless you already drew it. And if you did, don't worry about it. I just want to make sure that it's good notes for the homework. So you know what I'm going to do? Instead of going to the 1, I'm going to go to the 2. Just like that. It really doesn't make it any more difficult. It just makes the graph, you know, stretch vertically. And here's a true proof of the fact that a vertical stretch is not the same as a horizontal shrink. I did not make this graph any skinnier, and the proof is the fact that the asymptotes did not get closer together. It just got taller within its asymptotes. But that's it. Isn't that great? Isn't that easy? Freaking awesome. My man.